Let us locate the stationary points and tell their nature in this function. We have the function here, x cubed minus 3x squared minus x plus 5. You're to find the coordinates of the stationary points and determine their nature. You should also find the coordinates of the point of inflection. Alright, now here, this is a cubic curve. It's going to be, well, this is a cubic function, and if you plot it, it will be cubic curve. It might look like this, it might look like this, and the stationary points, it's going to have two stationary points. That's where the gradient would be 0. Our tangent would be horizontal. Could be this. Could be like this. Alright. So we're going to find out where these stationary points are located and the nature. This one would be a maximum point. This one would be a minimum point. Or if it's like this, you'd have the minimum point here and the maximum point here. Now, what we're going to have to do is to differentiate to find the gradient function. Equate it to 0 in order to find the location where the gradient is 0. And then we're going to have to use a method to determine whether it's minimum or maximum. We're going to use the second derivative method. So let's go. We're going to find f prime of x. So what we have here is 3 x squared using the power rule minus 2 by 3x. This will be minus 1. So we have 3x squared minus 2, 3 is 6x minus 1. So f prime x, the gradient function. Now, to find the location of the stationary points, you have x, 3x squared minus 6x minus 1 equals 0. Alright, we need to solve this. I don't think this can be factorized, so let us use a quadratic formula to solve it. So x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. What is b? B is negative 6. So negative b would be minus negative 6, which would be positive 6. So here, this would be 6. 6 would come here. B squared, b is negative 6. Negative 6 squared is positive 36. 6, 6, 36. So this would be 36. Minus 4 times a. A is 3. So it's minus 4 times 3. Times c now. C is negative 1. So this is times negative 1 over 2 times a. A is 3. So let's change the a to 3. Alright, so what we have here is x equals 6 plus or minus the square root of 36 minus 4 3 is 12, negative As 4 3 is 12. 12 by negative 1, negative 12 minus negative 12, which is the same as plus 12 over 326. So this is 6 plus or minus 36 plus 12. 6 and 2, 8, 3 and 1, 4. That's the square root of 48 over 6. So 6 plus the square root of 48 over 6, and then minus 1. In one case it's plus, in the other case it's minus. So it's 6 plus the square root of 48, that gives you that, over 6 equals 2.155. So it's 2.155, and also x plus the square root of 48, or x minus the square root of 48, we minus this time. So it's going to be 6 minus the square root of 48, will give you that, divided by 6 equal negative 0.155. So it's negative 0.155. Alright, so the stationary point would be located at 2.155 and negative 0.155. Okay, good. So let's make a note of the locations. So you have 2.155, and so it's located at x equals, let me erase part of this thing here. It's located at x equals 2.155 and x equals negative 0.155. Those are the locations. X is 2.155, x is negative 0.155. Now, their nature, the nature of these stationary points. We already have the second derivative here. Let's just erase part of what we did before. We have the first derivative here, I should say. We're going to use the second derivative, right? Find f double prime x. F double prime x equals 3 2's 6x minus 6. You differentiate one, you get 0. So it's 6x minus 6. Alright? Now, let us substitute 2.155 into this, as well as negative 0.155 into this, and see. Now, f double prime of 2.155 equals 6 times 2.155 minus 6 equal. What is that? Let's see. 6 times 2.155 minus 6 equal, it's a positive, so it's 6.93. So this is 6.93. What about f double prime of negative 0.155? What is that equal to? It's going to be 6 times negative 0.155 minus 6 equals. So let's see what happened here. 6 times 0.155 equal is negative, so it's going to be a negative, right? Why did I close the bracket here around the 6? The bracket should not close here. The bracket should close here. Alright, so back to our calculator. We have negative 0.93. Let's do it again. So it's 6 times negative 0.155 equal negative 0.93 minus 6. We have a negative 6.93 and negative 6.93. Alright, now the fact is, right here we have at 2.155 we have a positive 6.93. Now it shows that we have a local minimum point at that point. Why? Because since the second derivative is positive, it means as you go from left to right, the gradient of the tangents are increasing. If we should draw some tangents here, the gradient would be increasing, getting more and more positive, right? The right hand side of the tangent would be swinging upwards. It goes from negative to less negative, more positive as you go from left to right. And then at this point, at negative 0.155, you have a negative gradient. It means that you're going to have a local maximum point. Because as you go from left to right, if you should draw some tangents, you'll see that the gradient of those tangents would be dropping, would be decreasing. Alright, so if I should have my graph, this is my y-axis and my x-axis. What this is suggesting is this. At negative 0.155, you have a curve like that. At positive 0.155, at positive 2.155, you have this happening. Alright? We're not really sketching the curve accurately. Maybe the curve is somewhere down here. But whatever the case is, we're not really interested in, at this time, in finding all the intercepts and the exact location in terms of coordinates of these. So we just asked to find the location and the nature of the stationary points. Alright, so here we can say that the stationary point that is located at x equal 1.555 is a local minimum point, and that negative 0.155, it is a local maximum point. Alright, so that's what we have. Let's erase some of what I drew here and continue. Here now, we need to find the point of inflection. The point of inflection. So, in that case, the point of inflection, right, if the curve is like this, it's going to be some point here where on the left what you have is a concave upward part of the curve, and on the right of this point is a concave downwards, right? So right at this point is where you have a switch from concave up to concave down, right? Now if you should draw some tangents to this curve, these tangents would be having their gradient go from positive to negative, right? But after you pass the point of inflection, they start going from negative back to positive. They start going from negative to positive when you draw these tangents. So that's what happened at the point of inflection. Now, of course, alright, we have our curve. The way it's going to look, you have a maximum point at negative 0.155 and a minimum point at 2.155. So you're going to have a point of inflection somewhere between them, right? Somewhere here. So what we do in this case is look at the second derivative and equate it to 0. So let's do that. The point of inflection is going to occur where f double prime x equals 0. That is 6x minus 6 equals 0. Now when 6x minus 6 equals 0, what do you have happen? 6x is going to be equal to 6, and then you divide by 6. So x equals 1. Alright? So if x is 1, and we want to find the coordinates, what we need to do is substitute 1 into this. So we have x cubed minus 3x squared, x cubed minus 3x squared. So for x cubed minus 3x squared, looking back at the function, minus x plus 5. Minus x plus 5. That is f of x. So now f of 1 would be 1 cubed minus 3 by 1 squared minus 1 plus 5, which is 1 minus 3 minus 1 plus 5. 1 minus 3 is negative 2. Negative 2 minus 1 is negative 3. Negative 3 plus 5 is 2. So f of x is 2. F of 1 is going to be 2. So it will be at x equal 1, and f of 1 is 2. So coordinates will be 1, 2. 1, 2. So let's write that down. 1, 2. Alright, so there we have that. Suppose we plot this graph. What would it be? What would it look like? Alright, let's open GeoGebra, our graphing program. Plot the graph and see if we're really on track. This would confirm what the graph looks like. What the graph looks like. So x cubed minus 3x squared. So we have x to the power of 3 minus 3x to the power of 2 minus x plus 5 minus x plus 5. Bam. Alright. In fact, let me kind of fix up the curve. Yeah, the color is okay. I like to see the function that we're plotting. Let's make it thick. Alright, let's take a closer look at this thing. We said that the one of the stationary points is at negative 0.155 and its maximum. So a stationary point is at negative 0.155 and its maximum. It is maximum. Alright. Stationary point looks about here. Right. And it's a maximum point. It's on the top of a hill. So it's a maximum point right here. The other one is located at 2.155 and it's a minimum point. 2.155. Okay. You can see that it's a little past 2. It's 2.155. And it's a minimum point. You can see that. So it's 2 point something, less than 2.2. So you can see it. 2.155 and it's a minimum point. It's in a valley, so it's a minimum point right here. And then the point of inflection. Alright, let's see the point of inflection. We said that it's located at 1, 2. Where would 1, 2 be? 1, 2 would be the point right here. Okay, good. And you can see the swing will happen right there. Right, the swing would happen right there where you have, this is 1, 2, 1, 2 is here. So we have this point, alright, point A. Make the point bigger. So that's the point of inflection, where you go from having the gradient falling to the gradient starting to rise again, right? So you go from concave upwards, concave upward would be along here, to concave downwards. So you go from a cup to a saucer, right? Or from a hill to a valley. So that's what you have there. So that's it for now for this video. I will see you in the next video.